Audio Jungle. Audio Jungle.
Describe. A. Detector responsivity or dynamic range. B. Spectral response range or bandwidth. C. Response time. D. Receiver sensitivity. 1. Digital transmission bit error rate. 2. Analog transmission signal noise ratio. Responsivity. Responsivity measures the input-output gain of a detector system. Spectral response. Spectral sensitivity is the relative efficiency of detection of light or other signal as a function of the frequency or wavelength of the signal. It is the ability of a photoconductor to give response to the incident light of different wavelengths. Hence, the spectral response of the detector should match the spectral curve of the optical source. Response time. The response time is determined by two factors: drift of the electrons and holes that are photogenerated in the depletion layer. Diffusion of the electrons and holes that are photogenerated in the diffusion regions. Drift of the carriers across the depletion layer is a fast process, given by the transit times of the photogenerated electrons and holes across the depletion layer. Diffusion of the carriers is a slow process, caused by the optical absorption in the diffusion regions outside of the high-field depletion region. Diffusion current can last as long as the carrier lifetime equals greater than a long tail in the impulse response of the photodiode equals greater than a low-frequency fall-off in the device frequency response. Receiver SENSIVATY. The signal that corresponds to a prescribed value of the SNR. While the minimum detectable signal corresponds to a receiver sensitivity that provides SNI equals 1, a higher value of SNR is often specified to ensure a given value of accuracy, e.g. SNI equals 10103 corresponding to 10 to 30 decibels. For a digital system, the receiver sensitivity is defined as the minimum optical energy or corresponding mean number of photons per bit required to attain a prescribed BER. Signal-to-noise ratio (SNR). The ratio of the total signal to the total noise shows how much higher the signal level is than the level of the noise. It is a measure of signal quality. The signal-to-noise ratio (SNR) at the output of an optical receiver is defined as the ratio between the signal power and the noise power and presented as follow. 2.5.1 Explain noise factors. A. Thermal or Johnson noise. B. Shot noise. C. Dark current noise. Noise factor. Noise is unwanted components of the signal that tend to disturb the transmission and processing of the signal in a physical system. Noise generated by the photodiode is most critical. The three most predominant types. 1. Thermal noise, a noise due to the random motion of electrons or dissipation of heat in the detector resistance. 2. Shot noise is a small current produced from the randomness of the photon-to-electron conversion. 3. Dark current noise is a very small current present when no light is incident on the photodetector. Thermal noise. This is the spontaneous fluctuation due to thermal interaction between, say, the free electrons and the vibrating ions in a conducting medium, and it is especially prevalent in resistors at room temperature, where K is Boltzmann's constant, T is the absolute temperature and B is the post-detection electrical bandwidth of the system, assuming the resistor is in the optical receiver. Shot noise. Shot noise is a small current produced from the randomness of the photon-to-electron conversion. Any photocurrent generated, dark or otherwise, will have a shot noise mechanism associated with it. Because the multiplication factor, avalanche photodiodes have higher shot noise than other devices. Dark current noise. Dark current is a very small current present when no light is incident on the photodetector. This reverse current is caused by surface recombination and bulk leakage from thermally excited electrons present in the depletion region. This dark current noise increases with both temperature and applied voltage. Point 7.1 Investigate types of connector in fiber optic system. A. Ferrule connector FC. B. Straight tip street. C. Subscriber connector SC. D. Lucent local connector LC. 2.7.2 Explore types of adapters used in fiber optic system related to 2.7.1. Types of connector in fiber optic system. Fiber joints. Connections. A fiber joint is the point where two fibers are joined together to allow a light signal to propagate from one fiber into the next continuing fiber with as little loss as possible. Fiber joints fall generally into two categories: the permanent or fixed joint that uses a fiber splice, and the terminating non-fixed joint that uses a fiber optic connector. Splices are used as permanent fixtures on outside and inside plant cables. Typical uses include reel ends, pigtail vault splices, and distribution breakouts. In addition to the benefits of low loss and high mechanical strength, additional considerations are expense per splice and possible reusability of the splice itself. Fiber optic connectors are used as terminating fixtures for inside plant cables, outside plant cables as they terminate in a central office, interfaces between terminals on LANs, patch panels, and terminations into transmitters and receivers. Whether one joins fibers using splices or connectors, one negative aspect is always common to both methods: signal loss. This loss of light power at fiber joints is called attenuation. FC connector. FC optical fiber connectors were designed specifically for telecommunication applications. FC was one of the most popular single-mode connectors for many years. It also uses a 2.5mm ferrule, but some of the early ones use ceramic inside stainless steel ferrules. It screws on firmly, but you must make sure you have the key lined in the slot properly before tightening. It's been mostly replaced by SCs and LCs. Saint connector. Saint straight tip. Very popular for both data communication and telecommunication applications. Saint is probably still the most popular connector for multi-mode networks, ca. 2005, like most buildings and campuses. It has a bayonet mount and a long cylindrical 2.5mm ceramic, usually or polymer ferrule to hold the fiber. Most ferrules are ceramic, but some are metal or plastic. A mating adapter is used to mate two connectors. STs are spring-loaded. You have to make sure they're seated properly. If you have high loss, reconnect them to see if it makes the difference. SC connector. SC is a snap-in connector, also with a 2.5mm ferrule that is widely used for its excellent performance. SC connector was developed by NTT Nippon Telegraph and Telephone of Japan. The connector is mated by a simple snap-in method and can be disconnected by pushing in on a tab and then pulling the connector off. It was the connector standardized in TI-568 but was not widely used at first because it was twice as expensive as a street. Now it's only a bit more expensive and much more common. It's a snap-in connector that latches with a simple push-pull motion. It is also available in a duplex configuration. LC connector. Lucent developed the LC connector to meet the growing demand for small, high-density fiber optic connectivity on equipment bay, in distribution panels and on wall plates. Two common and proven technologies were combined in LC connector. RJ-45 telephone plug interface. Ceramic ferrule technology. LC is a small form factor connector that uses a 1.25mm ferrule, half the size of the SE. Otherwise, it's a standard ceramic ferrule connector, easily terminated with any adhesive. Good performance, highly favored for single mode. Adapters. An adapter is used to align the two fiber ends. An adapter also can be used to mate one type of connector to another. Two popular adapter designs are the straight sleeve and a biconical or tapered sleeve mechanisms. In the straight sleeve connector, the length of the sleeve and a guide ring on the ferrule determine the end separation of the two fibers. The biconical connector uses a tapered sleeve to accept and guide tapered ferrules. Again, the sleeve length and the guide rings on the ferrule maintain a given fiber end separation. Of these two cupping mechanisms, the straight sleeve connector is in much wider use. Apply splicing technique. 2.8.1 Expose splicing technique. A. Arc fusion splicing. B. Mechanical splicing. 2.8.2 Ascertain differences characteristics between arc fusion and mechanical splicing. Splicing technique. Splicing. A fiber splices a permanent or temporary low-loss bond between two fibers. Such a bond can be made by using either fusion splicing or mechanical splicing. Most splices are permanent and typically are used to create long optical links, or in situations where frequent connection and disconnection is not needed. Temporary splices may be necessary or convenient when one is making emergency cable repairs or doing testing during installation or troubleshooting. When the fiber bonding is done properly using high-quality equipment, the total splice loss typically is 0.05 to 0.10 decibels for fusion splicing and around 0.5 decibels for mechanical splices. Arc fusion splicing. In fusion splicing, two fibers are literally welded, fused together by an electric arc. Is done by an automatic machine called fusion splicer, which mechanically aligns the two fiber ends, then applies a spark across the fiber tips to fuse them together. Fusion splicing is the most widely used method of splicing as it provides lowest insertion loss and virtually no back reflection. Mechanical splicing. Mechanical splicing uses mechanical fixtures to join two fibers together end to end. Mechanical splicing join two fiber ends either by clamping them within a structure, by gluing them together, include transparent adhesives and index matching gels. Transparent adhesives are epoxy resins that seal mechanical splices and provide index matching between the connected fibers. In mechanical splicing, the assembly process involves stripping and cleaving the fibers, inserting them into a splice mechanism until they touch, and then securing them in place. The securing process is done by either clamping the fibers or gluing them to the splicing structure. To prevent light reflections within the splice, a special gel that has a refractive index close to that of glass can be injected into the space between the spliced fibers. This material is referred to as index matching gel. Most mechanical splice structures consist of a thermoplastic housing that is versatile and accepts fibers ranging in size from 250 to 900 micrometers. The goals of mechanical splice manufacturers are to have splicing structures that allow easy and quick assemblies of less than a minute or two after the fibers have been cleaved. Ideally, the assembly should require no heat shrink, curing, crimping, or gluing in order to reduce installation times and cost. Apply arc fusion splicing. 2.9.1 Write step-by-step the procedure of fusion splicing using splicing machine. 2.9.2 Apply safety precaution in performing the procedure in splicing to avoid hazard. Fusion splicing methods. Fusion splicing is the method of joining two optical fibers end-to-end using heat. The goal is to join the two fibers together in such a way that optical signal passing through the fibers is not attenuated or reflected back by the splice. The splice and the region surrounding should be almost as strong as the fiber itself. The source of the necessary heat is usually an electric arc. The following steps are necessary to splice optical fiber. 1. Clean the fiber. 2. Stripping the coating off the two fibers that will be spliced together. 3. Cleaning of the stripped fiber. 4. Each fiber must be cleaved so that its end face is perfectly flat and perpendicular to the axis of the fiber. 5. Aligning of two end faces of the fibers. This is normally done by the splicing machine by means of fixed V-groove, optical core alignment, cladding alignment, or local injection and detection of light lid. 6. The two fibers are fused together. 7. Visual inspection of the splice and splice loss estimation available on most splicing machine. Redo the splice step 1 to 7 in case an error is found. 8. Check mechanical strength of the splice, normally done by the splicing machine. 9. The bare fiber area around the splice is protected with a splice protector. Alternatives to fusion splicing include using optical fiber connectors or mechanical splices, both of which have in general higher insertion losses, lower reliability, and higher return losses than fusion splicing. Fiber optic installation safety rules. 1. Keep all food and beverages out of the work area. If fiber particles are ingested, they can cause internal hemorrhaging. 2. Wear disposable aprons to minimize fiber particles on your clothing. Fiber particles on your clothing can later get into food, drinks, and/or be ingested by other means. 3. Always wear protective gloves and safety glasses with side shields. Treat fiber optic splinters the same as you would glass splinters. 4. Never look directly into the end of fiber cables, especially with a microscope, until you are positive that there is no light source at the other end. Use a fiber optic power meter to make certain the fiber is dark. When using an optical tracer or continuity checker, look at the fiber from an angle at least 6 inches away from your eye to determine if the visible light is present. 5. NLY work in well-ventilated areas. 6. Contact lens wearers must not handle their lenses until they have thoroughly washed their hands. 7. Do not touch your eyes while working with fiber optic systems until your hands have been thoroughly washed. 8. Keep all combustible materials safely away from the curing ovens. 9. Put all cut fiber pieces in a safe place. 10. Thoroughly clean your work area when you are done. 11. Do not smoke while working with fiber optic systems. Bare fiber safety. However, fiber optics installation is not without risks. As part of the termination and splicing process, you'll be continually exposed to small scraps of bare fiber cleaved off the ends of the fibers being terminated or spliced. These scraps are very dangerous. If they get into your eyes, they are very hard to flush out. The ends are extremely sharp and can easily penetrate your skin. They invariably break off and are very hard to find and remove. Most times, you have to wait for them to infect and work themselves out, which can be painful. Wear safety glasses at all times when working with bare fibers. Be careful not to stick the broken ends into your fingers. Dispose of all scraps properly. You can keep a piece of double-stick tape on the bench to stick them to, or put them in a properly marked paper cup or other container to dispose of later. Do not drop them on the floor where they will stick in carpets or on shoes and be carried elsewhere. Do not eat anywhere near the work area. Other considerations: fiber optic splicing and termination use various chemical cleaners and adhesives as part of the processes. Normal handling procedures for these substances should be observed. Even simple isopropyl alcohol used as a cleaner is flammable and should be handled carefully. Note that fusion splicers use an electric arc to make splices, so care must be taken to ensure no flammable gases are contained in the space where fusion splicing is done. Smoking should not be allowed around fiber optic work. The ashes from smoking contribute to the dirt problems with fibers in addition to the possible presence of combustible substances.